I think good afternoon, ladies and gentlemen. My name is Daniel Moketi from Center for High Performance Computing. I'm a senior research scientist there, responsible for the astrophysics program and also lead the human capital development. I'll be sharing this afternoon session on behalf of Francesco. We actually work together because we are the main organizers of the event. So Francesco is having another agent meeting of Centers of Excellence. So our speaker this afternoon is Dr. Ilya Sinayskiy from University of KwaZulu-Natal. Who will be presenting about the open quantum system, introduction to open quantum system. So if you have any question, you know the protocol already, the procedure, you post it on the chat, and if it's very urgent, you want to interact maybe towards the end, so we'll give you an opportunity to do so. Over to you, Ilya.
Okay, Daniel, thank you very much. Hi, my name is Ilya Sinayskiy, yes, and I'm from University of KwaZulu-Natal. I'm working with Francesco, and the purpose of these 5 lectures will be to give you a kind of a very probably patchy, because 5 lectures is not enough, but kind of introduction to the theory of open quantum systems. And my plan is that on every lecture, I'm going to give you I'm going to talk about some of the aspects of the theory, and kind of ideally what I will be striving for is like 45 minutes of a little bit of lecturing, and afterwards 45 minutes of a little bit of programming. And you might see that the first tutorial is already I just uploaded to the folder on the Moodle website, but we'll go through that tutorial just now after we finish kind of a generic introduction. The trick will be that I'll try to share my iPad screen and write on it, so that the idea is that probably today I won't manage to do too many derivations because it will be generic introduction, but next time I plan to do a little bit of derivations, and so that to make sure that you can follow me, I think it would be much better if I'm going to write, because if I'm going to just present you some slides, you're going to be lost like after a few slides. Okay, let me try to share my screen, and I will try to, let's see how it goes. Okay, I assume that everybody could see my screen or my kind of iPad screen. And right now what I could see that I don't see the chat. So if you have some question, maybe, raise your hand, because I could only see my iPad screen and I could see the list of participants. I don't see the chat. Okay, so what we're going to do, we're going to do the introduction to theory of open quantum systems. Okay, and the first question is why we would like to do that. So I need to tell you a couple of words about the motivation, and the motivation is very simple. Theory of open quantum systems, or OQS, is quantum mechanics plus thermodynamics. Okay, so from your standard university course on quantum mechanics, and I would assume here that most of you have a kind of idea of standard quantum mechanics, or in the worst case scenario, like atomic physics, because I'm going to operate with the things like Schrödinger equation, and afterwards some kind of further modification of this equation, which is called quantum master equation. But for that, you need at least seen a couple of times in your life Schrödinger equation. Okay, so, and as you know from standard course of quantum mechanics is inherently time reversible. Yes, so if you write Schrödinger equation, which I can write for you just now, yes, so IH deep psi of t by dt is equal to I from psi of t, where h is the Hamiltonian. Yes, so kind of we can go backwards in time, we can go forwards in time, and it doesn't really distinguish it. There is no error of time in quantum mechanics. That, as we all know, error of time exists. Yeah, so kind of, you know, when you have your cup of coffee or cup of tea, it's cooling down. It's don't simultaneously begin to heat up. So, and the idea of the theory of open quantum system, what does it do? It's exactly put the idea that, you know, your cup with coffee will cool down together, but on the quantum mechanical level. And the first question is, do we really need it? Is it really relevant? Because, you know, it could be, it's important for the coffee and it's important for the, I don't know, some other events or some kind of other thermal phenomena, but it's completely irrelevant for quantum mechanics. And the answer is no, it's relevant. And the very, very simple example, which everybody came around, is consider an atom. Yeah, and let's excuse me for the drawing you atom as the, you know, we have some positive nucleus, and of course we have an electron flying around. And of course, it's not flying around, it's distributed as the wave function, kind of, and so on and so forth, all the standard things. But now this atom is in some excited state. So the electron in this atom is an excited state. And according to the laws of quantum mechanics, if I fix the electron here, so if I excite the atom to excited state, it will stay there forever. But experimentally, we know that whatever we do, what will happen, that the electron will go back. Always. Even if we put this atom at the zero temperature environment. And this is the most interesting thing out of that. So like, even if there is no zero temp, and when I'm talking about zero temperature, I'm talking about 0 Kelvin, so minus 273,15 Celsius. Yes, so kind of, we are an absolute zero, but still your excited atom will emit photon and go to the ground state. And the question is why? And the answer is very simple, and the answer could be done by the theory of open quantum system, because your atom is interacting with world around it, which in this case is represented by vacuum, which is at the zero temperature. So essentially what is happening, this interaction is leading, it's essentially forcing atom to emit the photon and go to the ground state. And because the environment is at zero temperature, that photon could not go back, or extremely unlikely to go back to atom to re-excite it. However, process like that's happening, and this is happening when your system is interacting with external environment strongly. Whatever this means, and what does it mean, we're going to talk a little bit later. And kind of, you can ask a natural question. Do we really, again, it's like, why do we study quantum mechanics and never talk about that? Or at least usually in the standard course of quantum mechanics, I don't know if you open the Griffiths or open many other books, in the kind of only recently, in the last probably 10 or 15 or 20 years, people begin to add in the end chapters which are related to the phenomena which is called dissipation and decoherence. And the question is why? And the answer is, it's only, first of all, quantum mechanics is difficult enough without temperature. And with temperature, it's more difficult, but it's also the question of the time scales. So if you do, or if you study quantum mechanics on the time scales on which thermalization or equilibration is not happening, or kind of on the time scales which are much faster than the time scales than interaction with environment, in that case, you don't need thermal phenomena, because you can do everything much better or much faster, so time scales. So if you can do things much faster than, so if your kind of typical time scale in your system is much, much smaller than the time interaction with the bath or environment, you can ignore thermal phenomena, because you can do things quick enough so that temperature or interaction with some external phenomena kind of doesn't bother you at all. But usually it's very difficult, especially now when we want to build some devices or realistic devices which are using quantum mechanics. For example, we want to build a quantum computers. And one of the most severe obstacles which why we still don't have something which is called fault-tolerant quantum computer, is dissipation and decoherence, that the interaction with environment is essential part of the realistic physical setup, which we always need to take into account. Okay, so let me now tell you a couple of words. I mean, first of all, is there any questions about generic motivation? Because my plan is next, I'm going to tell you about what are we going to talk about during these 5 lectures, which kind of what literature I can recommend. And afterwards, we'll also speak about a couple of words about some basics of quantum mechanics and what kind of equations we're producing in the simplest case in theory of open quantum systems. Okay, so my plan is the following. So during today's lecture, what I'm going to give you will be general introduction. We're going to set up some vocabulary which we're going to use. And originally I was planning to show you a macroscopic derivation. So because I'm going to just postulate to you that for these classes of situation, the following type of equation is going to happen. And the equation is a little bit bulky, kind of to derive it in general way. It's possible, it's not too difficult, but it's a little bit bulky. So I was planning to derive it in a simplified situation, but now I think I probably won't manage. And what else I want to do today is I want to give you some very elementary examples of solving master equations. So that's what the Schrödinger equations become when you take into account temperature in Python. So that will be the part in the tutorial. So in the second lecture, what I want to talk with you about, I want to give you a microscopic derivation in one of the very simple cases which we're going to consider today in the tutorial. Plus, we're going to talk about quantum channels. And quantum channels is one of the ways how we can describe open quantum systems. And of course, in the tutorial part of that lecture, we're going to have some examples and we're going to see how we can encode evolution into the quantum channels, and we're going to consider some properties of quantum channels. On the third lecture, I plan to present to you some other approach to the open quantum systems, which is called quantum trajectories. And quantum trajectories allows you to to have a different description of the interaction with environment. And for that, we will need to talk a little bit about stochastic analysis or stochastic processes. And I'll probably start with something like Brownian motion, just kind of classical Brownian motion, and show you how very similar ideas can be brought to the quantum mechanical world, and how can we play that game. And of course, in this case, we can also have some tutorial where we're going to first to play with a classical Brownian motion, and afterwards see how we can perform so-called unravelings and how we can construct trajectories. Okay, so on the fourth lecture, I plan to talk with you about to make a little bit of connection between theory of open quantum systems and quantum computing. So what I plan to do, I'm going to demonstrate you how to do digital quantum simulation of open quantum systems. So what does it mean? I'm going to show you how we can use quantum computer, if we have one, to simulate open quantum systems. And in fact, we have very small ones, which doesn't allow to to give you any real advantage, but to these machines we have access. And we are going to talk about this in a framework of so-called Qiskit. It's a Python package from IBM, and IBM allows you to access for free to these quantum devices, which are very small. So usually it's like 5-qubit devices, or there are some, I think, 14-qubit devices. And if you belong to the if you're a student in South African public university, and if this university is a member of ARUA, which is an association of the African universities. And to the best of my knowledge, all big universities, at least University of KwaZulu-Natal, Wits, Pretoria, Stellenbosch, UCT are members of that network. So you can get access to the kind of to the kind of institutional access to the IBM devices, which will give you access to the 27 and 65 qubit machines, and you can do experiments on that machines. Okay, so that would be lecture 4, and on the lecture 5, because mainly what we are going to deal in these 4 lectures will be related to mostly to the very finite dimensional system. So we're going to deal with a single qubit or kind of single 2-level system or couple of 2-level systems, but kind of quite a small systems. In lecture 5, we're going to give a look into what's happening when you are dealing still with a few system with a few degrees of freedom, but formally infinitely dimensional, called quantum harmonic oscillator. And we're going to use the quantum harmonic oscillator after we kind of talk about how to describe dissipative dynamic of quantum harmonic oscillator. I plan to talk with you about something which is called James Cummings physics. And James Cummings physics is kind of James Cummings model is the fundamental model which describes to you interaction of the light and radiation, or light and matter. Light will be a quantum harmonic oscillator, as you know from your standard quantum mechanics course, and matter will be just a 2-level systems, and we're going to see how can we solve this kind of mass equations for James Cummings, for the dissipative James Cummings model. Okay, so now that's how the plan of the lectures is looking like. And now let's go to what can you read if my lectures are not enough, or if you decide that you want to use open quantum systems for something for your research. And so kind of books and papers. Okay, so book number 1 is clearly what it would be. That would be a book co-authored by Francesco. It's a very famous book in the field. So Breuer and Petruccioni. And as you can guess, it's called exactly Theory of Open Quantum Systems. It was published in 2002, and by 2002, it was the kind of state-of-the-art book. By now, it's a little bit like almost 20 years old. So kind of there are new developments in the field, which that book doesn't cover, but the book, I mean, covers most fundamental things. Okay, I see that there is a one in the chat. Please, the link to the IBM. That's very simple. Link to the IBM, you just type in the Google IBM Quantum Experience, and you get the link. Okay. So the next book is much smaller, and the beauty is that the kind of the pre-published version of this book is available for free in the archive, which is the server for the academic publication, and it's written by Rivas and Huelga, and it's called Open Quantum Systems, an Introduction. And it was afterwards published by Springer, but as I mentioned to you, if you just go to the webpage archive.org/ABS for the abstract, and the identifier is 1104.5242. You can get this book for free, which will be quite close to the published version. Yeah, absolutely correct. Yeah, quantumcomputing.ibm.com. Thank you. Thank you, Marisa. Okay. So what else? So on the stochastic side, I can recommend, there is a kind of standard book, which is written by Van Kampen many years ago, which is called Stochastic Processes in Physics and Chemistry. And it's a very good introduction into the theory of the stochastic processes, irrelevant classical or quantum, so the both are covered. And on the side of the pure quantum stochastic processes and how to deal with the quantum master equations, due to some historical traditions, these methods were first developed in the quantum optics. And there will be a bunch of books which I can recommend you, which are related to the usually quantum optics plus stochastic processes. So quantum optics plus stochastic processes. And here there is a bunch of extremely good books, and you don't need to read them all. You can choose whatever you prefer, but I think they are all very good. So first book is by Gardner and Sola, and it's called Quantum Noise. Next book is by Harvard Carmichael, and it's called Statistical Methods in Quantum Optics. And this book have 2 volumes, but for the generic purposes, you want to stick to the volume 1, and in volume 2 there are some advanced applications. And there is also a very nice book by Walls and Newburn, and it's called Quantum Optics. And I mainly list for you here the books where there are a lot of books about quantum optics, on quantum optics, but usually it wouldn't have a very strong open quantum system components. These books have a very serious and well-developed components on the theory of open quantum systems in application to the quantum optics. And in case of this book, it have its how to say limitations. For example, because Harvard Carmichael consider quantum optics with the light and matter, real light and real matter, in the sense matter in the sense of 2-level systems interacting with, I don't know, visible light or radio frequency light. And these kind of approaches are inherently Markovian due to some reasons. And what does it mean? I will tell you a little bit later. While in the Gardner-Sola book, what you see that he also considered so-called non-Markovian approaches, which are also quite interesting now, not for the real atoms and interacting with visible light, but for example, in artificial systems, in so-called circuit quantum electrodynamics, where people consider how to create systems which behave, essentially it's a Josephson junctions, or superconducting systems, but you can tune them in such a way so that they behave as a 2-level system. And afterwards, you can couple them not to the visible light, but you can couple them to the something which is called transmission line resonator, and that sort of resonator behave at the certain intensities. When the intensities are low enough, it's quantized and it's behave like a harmonic oscillator, and they interact exactly in the same way as your James Cummings model will describe you. But in that case, you can go far beyond the regimes which people see in the traditional quantum optics. And for example, Howard Carmichael doesn't cover that, but for example, Peter Zoller covered that in the newest edition of the Quantum Noise book. Okay, so if you are interested in quantum channels, so very basics of quantum channels, which will probably allow you to go through this course and maybe do something very simple things you can get from the standard textbook on quantum computation, which is written by Nielsen and Chan. And it's called Quantum Computation. and quantum information. And there is a chapter on so-called quantum operations where they introduce the theory of quantum channels. Okay, if you want more deeper dive into the theory of quantum channels from the formal mathematical standpoint, there are wonderful free lectures on the internet written by Michael Wolff, and they're called Quantum Channels. And operations, guided tour. So if you just type in Google, Wolff, quantum channels, guided tour, you're definitely going to get the PDF from his webpage where this kind of set of notes is available for free and regularly updated as much as it's possible. Okay, so in the part of digital quantum simulations of open quantum systems, but in general, of course, Nielsen and Chan, quantum computation and quantum information, so the book which I reference here, but also you have a Qiskit tutorials. Qiskit is the, as I mentioned to you, is the package to work with the IBM quantum computers, and it's have very kind of community friendly and well developed tutorials. And the resource which I will use for my part of the lecture will be related to the paper which was recently published by the group of Sabrina Maniscalco. And it's called IBM-Q Experience as a versatile testbed, but essentially its archive identifier is 1906-07099, and it's also published in the journal which is called NJP Quantum Information. It's issue 6, page 1, and it was published in 2020. So this paper, as well as archive, is of course available for free. This paper is also available for free, so you can download the published version of the paper. So you just Google, you can Google this identifier, or you can Google NGP Quantum Information 6/1/2020, and you're going to get the link. You can give a look into the paper after the lecture or before the lecture, and you can kind of go on. And what is also very interesting related to this paper, that they have a very nice, so here there is very nice GitHub repository with the all codes which they were using for simulation of the quantum computer. Okay, so that's probably it about the literature. And now we're slowly coming to the subject matter. So do we have any questions by whatever I told you now?
Seems like no questions so far.
Okay, okay, fine. But so far there was nothing of substance, so to say. Okay, let's start to the substance. Okay, so what are the basic assumptions of the theory of open quantum systems? And they traditionally are looking like this. So we have a system and we have a large environment or thermal bath. So, and what is the typical difference which you can make and say, okay, this is clearly the system and this is clearly the environment. I mean, the separation is always like very fuzzy, and you can decide how you divide it as a function of, of your convenience. Sometimes you might take something from environment and put it to the system just to produce the simpler master equation, and in which sense simpler I might tell you just now. Okay, so, but generally system is characterized by the very few degrees of freedom. So it means that the system is typically spin, 2 spins, maybe 10 spins. So kind of for it could be harmonic oscillator or harmonic oscillator interacting with, your with your spin or your two-level system, but it's something which is relatively small in comparison to the bath. And it's something of your interest. So kind of this is your, so that's what you are interested in. You wanted to know how that this part of everything is evolving. What is bath? Bath is something which is obviously affecting your system. But first of all, you're not very interested in what's happening with the bath. Second, bath is usually having a huge number of degrees of freedom, something like 10 to the 23. And it's clear that, you know, even if there are some examples of exactly solvable models, you don't get too much information. You don't get too much useful information from the bath. Or even if you can kind of write equations, you can usually or typically you cannot solve them. So kind of the bath is something, a lot of degrees of freedom. And you just, what you want to know as a person who is building the model, or the experimentalist who is trying to do some quantum experiment and wanted to see how the environment is going to kind of, how environment is going to kind of prevent you from achieving your goals. Like, for example, you want to build a quantum computer and you want to know how the environment is going to decohere and dissipate whatever is happening within your system. So what you are interested in how the environment is affecting the dynamics of the system. And of course, I mean, the next question could be if it is like you want to do it for the optimal control or engineering. So you want to know how you can mitigate or how you can cancel out or compensate for the effects which is environment is pushing on your system. Okay, so and as in any, and that's why where you can see that's why some of the books which I recommend are called statistical approach, because it's a very statistical physics approach to the problem, so that you have a small system and you have a large bath. And if you remember something which is called canonical ensemble in statistical physics, that's exactly kind of quantum version of that's what you are going to study, or kind of you want to use the bath is something large, and you want to kind of just know how the bath is affecting your system. And also there will be kind of a standard set of assumptions, as I mentioned to you, and what you're looking for a kind of good enough solution. So if it's a good enough to consider that your system is very weakly interacting with the bath, you get one type of solution. If you need to, your situation is such that your system is interacting strongly with the bath, and you cannot just say that system is affected by the bath, but bath is unaffected by the system. In that case, you need to go to the other methods of description of the open quantum systems, which are getting more and more involved. The more degrees of freedom of the bath you want to incorporate in your model, not as just some coefficients, but as reasonable effects. So kind of you want to see what is the dynamics of the correlations between the system and bath, or what is the entanglement which is formed between the system and bath. This is usually happening in the strong coupling scenarios. Kind of your description and your kind of numerics are usually getting more and more complicated. Okay, so usually what is the typical assumptions which we are going to do? Usually we are going to assume, or kind of that the most part of these lectures is going to assume something which is called weak coupling limit. Which is going to lead us to something which is called quantum Markov master equation. And if you want, you can add in Gksl form. So that's what we're going to mainly to focus on, where the Gksl is standing for Garini, Kazakovsky, Sudarshan, and Lingod, by the first letters of the surname of the people who first came up with the two separate publications with the existence of the such mathematical description. Okay. So, but before we formalizing this description, let's just very quickly run through some simple things. I assume that everybody knows some very basics of quantum mechanics, which I means the following. So some basics of quantum mechanics. So in quantum mechanics, everything is formulated on the language of the so-called wave functions, which are living in the Hilbert space. Yes, and these wave vectors in the Hilbert space, they are evolved by something which is called unitary transformation. So to go from the wave vector psi to psi prime, I apply unitary transformation. And of course, the unitary transformations has this nice property that they preserve the norm, also, so they conserve the norm of the wave function, such that so u dagger u is equal to u dagger is equal to identity. Okay, and as you know, so kind of this is high level way of writing unitary operator, but the low level of writing or kind of coming to the unitary operator, I already mentioned to you, it's called Schrödinger equation. So and standardly in the quantum mechanics course, so you also shown that if you have two wave vectors, psi of t and psi 0, you can always relate them by using the, again, unitary operator, but in this case, you choose this unitary operator in the special form so that it depends from two times, from this time and from this time. So formally, sometimes we will write T0 here, so we can do it or we can skip it. Okay, and if we just substitute it into this equation, we will get identical equation, because that equation should be for the all possible initial vectors. We'll get the Schrödinger equation, but for the unitary operator, where the, of course, initial conditions is that unitary operator at time moment 0, or if we use two time notations, sorry, u of 0, 0 is equal to identity. Yes, of course, because if we have here identity, in that case, if the t is equal to 0, we get exactly the same vector. Okay, so that would be very good. But what we else need, we need to have a way to describe, because we are not always dealing with the wave vectors or kind of wave functions. Sometimes we have to deal with the collection of the wave functions. And what do? We form something which is, we're dealing with something just called mixed states. Yeah. And in these mixed states, what we kind of, how they're usually produced, that you are dealing, that you're not having, so kind of, you have a box, and you know that in the box, you have, your system is prepared in some state. And if this state is a pure state or is described by the wave function, you're fine. But sometimes what you can have that with the probability P alpha, you know that you have some state psi alpha. And you have a collection of the states like this. And the question is, can you describe it by some in some way? And of course, that the density matrices or statistical operators, they give you a natural description. Of course, that's kind of as a definition, that sum of alpha, p alpha, psi alpha, and where they, of course, the sum over the alphas is 1, and p alphas, of course, are non-negative numbers bounded by 1. Okay, so, and this density operator will be our primary object of work, because there is very few examples where you can start with the pure state, and due to the interaction with environment, the system will remain in a pure state. It's happening, but it's happening extremely rarely for very exotic cases. Usually what you will have your system is starting in some state, and with some probability it's going to the one state due to interaction with environment, and with some other probability it's go to some other state. And so after a little moment of time, what you have a mixture of these two possible outcomes, which of course, after another small moment of time, are evolving into another mixtures. And as a result, you very quickly end up with having like a very many different states which are mixed together, and they're describing to you what is happening to your system. Okay, and again, I assume that most of you have seen it in a standard quantum mechanics course. But if not, just let me know, because I'm happy to give you a couple of examples. I'm not ready to give you a course on quantum mechanics here, but I can give you a simple examples if you see it for the first time. There are a couple of properties of the density matrices which are important for us. So density matrices are positive, so it means that they have a positive eigenvalues. So they are normalized, so trace is equal to 1, and they are Hermitian. So Hermitian conjugates of them are equal to themselves. Yeah. So and this is the 3 fundamental properties. Okay. So what is the equation of evolution for the density matrices? And the equation of evolution for the density matrices in the general case is called Liouville von Neumann equation, and it's essentially coming from the equation from the Schrödinger equation, or from the Schrödinger equation for the unitary operator. Yes, so kind of essentially you take this mixture, and if you have here some collection of initial states, you act from the left and from the right using the unitary operator, and you get a unitary dynamic, and you get time dependence of the density matrix. So U of t will be sum of alpha, p alpha, U of t psi alpha 0 on psi alpha 0 on U dagger of t. And of course, we can just take this u's outside of the sum, and we can get the generic expression U rho 0 U dagger. And afterwards, we can differentiate it by time. And after doing a standard transformation, we're going to end up with something called Liouville von Neumann equation. So d rho by dt is equal to minus E over H of your Hamiltonian and density matrix. So it's essentially, it is Schrödinger equation for density matrices. It's kind of completely equivalent. It doesn't have more information, it doesn't have less information, or in fact, it's have a little bit less information because it doesn't have information, it's have information only about no, it's have identically the same amount of information. No. Okay, now I'm cornering myself. Okay, so this is called Liouville von Neumann. And the only thing which I'm thinking about information is related to the phases, because the wave functions are defined up to the phase, but this global phase becomes completely irrelevant for the density matrices. That's the only thing. Okay, so this is a Liouville von Neumann. And what else do we need? We need the notion of the partial trace. I don't know, have you ever seen the partial trace or not? But this will be a very important operation, because this operation will allow us to come from the description of the system plus bath to the description of system only. And it works in the following way. So partial trace. So if you have your system, and your system have two subsystems, subsystem A and subsystem B. Okay, and so what you can have that your subsystem A have a basis vectors EA, subsystem B have a basis vectors JB. And for example, we're going to consider example of the two qubits. So your qubit could be in state 0, state 1, or in state, okay, in the tutorial, we'll use notation 1 and 2. Sorry, let me use it consistently, 1 and 2. System 2 is also have 2, so it's kind of two-dimensional systems, but of course partial trace is defined for arbitrary number of dimensions, but for the sake of the example, I'm going to show you two-dimensional systems. Okay, so and how can we represent, for example, wave function in this qubit space? So arbitrary wave function psi AB in this qubit space can be always written as the sum over I and J. Yes, so we just running by these indices, and we have some number Cij, tensor JB. Yeah. So now if we go to the density matrices, and that's what we're going to do, we'll get twice more indices. So kind of density matrix rho AB will be sum over Ij, I prime, J prime, and we have some numbers Ij, I prime, J prime, EA, JB, EA prime, and JB prime. Okay. So, and if it's a little bit counterintuitive, I will give you just now an example which probably can make you feel a little bit better. Okay, so and of course these coefficients or these numbers are chosen in such a way so that all the properties of the density matrix are satisfied. Otherwise, we're not dealing with the density matrices, or we're not dealing with the valid density matrices. Okay, and so density matrix rho A can be defined based on this definition as the partial trace over subsystem B. So we essentially are summing up all the degrees of freedom of subsystem B in the following sense. So now it's going to have in our expansion, it's only going to be expanded in the basis vectors of the system A, and the basis vectors in the system B are going to be summed up and traced out. So it's going to look like, so sum over I and I prime and sum over J. And what we're going to have here, or it's better to write even not like this, but the J, make it as internal sum over J, C, I, J, I prime, J. So essentially it's defined by taking some sum over diagonal basis vectors, sum over P and the B system. And here what will remains is only vectors in the kind of the basis vectors in the system A. So what do we get as a result? We get what will happen to this big system we described to us system A and system B, for example, 2 spins. So what will happen if I want to describe only one spin and I don't care what's happening to the second spin? So if I begin to measure this spin A and I don't care about what is happening to the spin B, what I can do, I could create a projection, or I could create a measurement, I could perform a measurement, but to describe it theoretically, I could have a measurement on the system A where I measure something like, for example, sigma E, an identity on the system B, or I could first calculate a partial trace and go from, if it's 2 spins, it will be 4x4 matrix. I could go to the 2x2 matrix, and afterwards already in there, do the partial measurements, and I will do it exactly according to these little rules. Okay, so how can we see it very nicely? So we can see it very nicely for an entangled state. So for example, we have a bipartite entangled state, so-called Bell state, which is looking like this: 1, 1 plus 2, 2. And kind of these classes of states are very interesting. They have a whole bunch of very interesting properties. And one of them is, of course, related to the fact that kind of this, okay, so to be consistent with my notations, I should write 1A, 1B plus 2A, 2B. That we can write it like this, but we can never write it as 2 local bases which are multiplied on each other. And this is kind of the fundamental property which is related to entanglement. But again, I assume that you've seen it in the standard course of quantum mechanics. And now what we can do, we can now trace what will be with the highly entangled states, which have all those interesting properties which are important for the quantum cryptography, quantum computing, if I'm just going to look on one of them. So what I'm going to see. So let's calculate what will be rho A, which will be traced over the B of psi AB, psi AB. And here we can write it explicitly, so that's why we're going to do it. trace over B. And what we have here, and let me, for the simplicity, write it like 1, 1 and 2, 2. So, but we respect the order. So 1, 1 plus 2, 2 on 1, 1 plus 2, 2. Okay, so now we're going to have 4 terms. But remember that now what we need to do, we need to take a sum where this index is equal to this index. Yeah. So what does it mean? It means that we get trace 1/2. So we need to take a situations. Okay. So where this index is equal to this index. So that term is going to give us something. But this term, because here is 1 and here is 2, there will be no term like this. So what we're going to have 1, 1, of course, in subsystem A plus, and what we're going to have here, so this term we already took into account. This and this are not going to give us anything, yes, because the indices are different, and only this and this is going to give us some positive contribution, or kind of some contribution at all. To B, so, oh, sorry, A. So what are we getting? We're getting just 1/2 of identity matrix. So instead of if we just taking and tracing out, so and that's kind of operation which happens, and you can also demonstrate it experimentally, for example, with linear optics and in many other settings, so that if you take a highly entangled state, but you trace out or you ignore, and you see how your what will be your description if you just ignore the half of your system. So in fact, you're dealing with extremely boring state. And by the way, yes, this state is, of course, can be written like this. Just 1/2 of the identity, when we essentially, what does it mean? It means that we have any idea about the state of the system, because we're saying with 50% spin is up, with 50% spin is down. Okay, so are there any questions about this, or can I go to the dynamical maps, or shouldn't I go to the dynamical? No, I cannot. Okay, I don't see any questions in the chat because I found how can I see the chat. Okay, so let me briefly mention to you a couple of things, and we can go to the tutorial, because all this was kind of relatively standard and basic. But now what I need to tell you, I need to prepare you to the macroscopic derivation on the next lecture. And for that, I need to introduce you a couple of things. Because why do we need Schrödinger equations or Liouville von Neumann equations, and why do we need the partial trace? Because now, if we wanted to describe open quantum system, yeah. So we wanted to start from some initial state, which is usually, or kind of traditionally, but not necessarily, because now people already considering different initial conditions, are considering that you have your system and your bath. And they are kind of do not interacting with each other until the moment 0. You turn on time and they begin to interact. However, now people also question this assumption, and there are papers where people are consider something which is called system bath initial correlations. But for our very basic purposes, we can consider that initially you prepare your electron or your spin in some state, and afterwards you let it evolve as a function of interaction with the environment, and you measure it, and afterwards you make some statement about how it was evolving, how was the probabilities of having spin up or spin down or behaving. Okay, so we can do the unitary evolution, kind of at least mathematically, and we ended up with a state like this. Yeah, so unitary. And afterwards, because this object is defined in a huge space, what we want to trace it over the bath, because we're not interested in what's happening to the bath. And we want to end up with only density matrix of the system. But as I mentioned to you, you can go this way from the point of the modeling, but it's very difficult. Sometimes it's impossible. and it's very impractical. So what people are doing much more often, so they go down here. So they trace over the path here, and what you have in this case, you get only the density, initial density matrix of the system. But now the question is, can you go from initial state to a final state? And if you can, how? And of course, the answer is the fact that I'm drawing to you these diagrams mean that the answer is yes, you can, not always, but in the most cases which we are interested in, you can do it, and you can construct something which is called super operator, or operator which is acting on the density matrices, which is going to describe to us evolution. So first of all, why it should be possible? It should be possible because of the very simple idea, so that we have here the density matrix of the system. So it exists as the operator over the Hilbert space, and we can define the basis in that space of the operators over the Hilbert space, and we can expand it in that basis as you expand your vector to the components. And afterwards, you can do the same game to your initial state, and afterwards you can relate those two vectors by the sum transformation. And that transformation will be exactly called dynamical map. And sometimes it's also called super operator, but in the classes of equations which we are going to consider, it's called dynamical map. Or if our initial conditions are uncorrelated, it's also called quantum channel. Okay, now the question is how you can build them, how you can construct them mathematically, which models can you use, how you do it. And that's exactly what we're going to talk about. And in order to talk about, we need to first, I need to tell you a couple of formal words. So what we're going to do, I mean, this guy in the very narrow wide classes of cases can be described by something which is called, it's belong to the family of the one parametric semigroups. And that one parameter is time. And whose semigroup? So some of you might, with a mathematics background, have seen groups and have seen the group theory. For example, those of you who have done, I don't know, nuclear physics or high energy physics with a standard model, you have seen the application of the group theory over there. While in theory of open quantum systems, you are dealing with the semigroups. And what's the big difference? Because you have something which is called the group composition law, which is a very simple statement, which means essentially the following thing. So let me write for you the group composition law. So if you have, so if it's one parameter, so I need to write it like this, T1 minus T2, it could be written as V of T1 minus S on V of S. So S minus T2 for all S's, which belongs to the interval T1 and T2. Okay, so it means that if you know how you evolve for some moment of time, you can always do the compositions. And it's identically in the same way it's working for the unitary operators. But the unitary operators which describe to you pure evolution, they belong to the group. There is a corresponding group which is defined on the vectors of the Hilbert space and so on and so forth. But these guys belong to a semigroup. And the big difference is that for semigroups, you not always have an inverse. And this is a very interesting and subtle difference which is related to the physics. And this is a very beautiful manifestation of the difference between theory of open quantum systems and quantum mechanics. Because in the groups, and so all unitary operators belong to some groups. In general case, it's called SUN, or special unitary n-dimensional group. You always have an inverse. What does it mean, always have an inverse? It means that you can always go forward in time and backwards in time, always. You can take any wave function and you can go in one direction in time and you can go reverse. But when you're dealing with open quantum systems, what are you describing? You're describing how quantum mechanics interacts with thermodynamics. And what does it mean? it means that, so what's happening to your cup of coffee when you leave it for a long enough time? It's cooled down to the temperature of your room. And what does it mean? It's mathematically. It means that now if you are sitting next to your cup, which is with the temperature of the room, there should be no way, and there is no way, how you can say what was your initial temperature. And what does it mean mathematically? It means that the inverse transformation, which take your cup from your kind of hot cup to the cup with the temperature of the room, you cannot inverse this transformation. And in quantum case, that's exactly will be a semigroup, because the inverse elements will be existing for the essentially all elements of the of your dynamic kind of for the all possible density matrices, except when you apply them to the steady states, or when you apply them when you thermalize to the temperature of the bath, you cannot go back. So if you come to the temperature with equilibrium with the bath, there is no information anymore available where you come from. So and that's why the inverse elements in these cases should not exist, and they don't, and that's why you need to deal with the semigroups. Okay, but with the semigroups, there is one more mathematical statement which I need to tell you, and we can go to the tutorial. Okay, so it was shown exactly in that Gksl papers, so by the Gorini, Kazakovsky, Sudarshan, and Lindblad. So this is two separate papers. So they have shown that, first of all, such semigroup generator exists, which is also non-trivial question. And they have shown that, that these guys, V of t, in the general case are looking like this. So that exponential of some generator, so that from this you can conclude immediately that the equation which density matrix for the system is satisfied is looking like this. So we can just differentiate it. But the important thing is that, because this is a rather generic statement. Important thing is that they say, okay, these generators have a particular form, and this form is still holds. So kind of they've done it in mid-70s, and so kind of so far that's the only form which have a set of very interesting properties which we are going to discuss in the nearest on the next lecture. So it looks like minus EH rho. So that's so far so good. So this looks like clearly von Neumann equation. And now we have the term which is looking like this. Sum over k from 1 to n squared minus 1. So if your Hilbert space is n-dimensional, so you have n squared minus 1 terms which are looking like this. Oops, sorry, I think I've got too much. Just move. AK rho s AK dagger minus bracket 1/2 of the anti-commutator AK dagger AK. Okay, so this square brackets is the commutator. Curly brackets is the anti-commutator. Gamma k's are greater or equal to 0. And of course, yes, anti-commutator AB is AB plus BA, and commutator AB is, of course, oops, AB minus BA. Okay, so when there is generic derivation, how you can, if you take any n-dimensional system, so you take any n-dimensional Hilbert space, that you can show that the corresponding under the kind of certain assumptions, you end up with a description of your interaction with the environment, which will be described by the such super operator. And again, why it's called super operator, because you see that here you have not only that kind of you apply operation to the operator, that's why it's super, but it's also very interesting that you get the terms which you haven't seen previously in Liouville von Neumann equation or in Schrödinger equation. So when your operator acts from the both sides, and this is a very important part of this equation, because this is so-called jump terms. These terms exactly describe to you what happens when the system essentially is given away or taking the energy from the environment, and this term have a, oops, sorry. There is a typo. Forget AKA row. Otherwise, there is no anti-commutator with anyone. Okay, so what we are going to do next time, we are going to show how to derive these sort of equations, not in this generic setting, but we're going to choose a model. And in that model, we're going to go all the way from the Hamiltonian of the system and the kind of suggestion how the bath might look like. And afterwards, we'll go all the way till we end up with an equation like this. And over there, kind of step by step, I'm going to tell you on each level which approximations we're doing, because it will be very interesting also from the point of view, like on some stage, what you're saying that you kind of, what you're introducing, which is not present in quantum mechanics, you're introducing irreversibility. So you're introducing error of time. So there will be a well-defined mathematical steps when you're saying that, okay, starting from this point, time can go only in one direction. And this is just a very interesting thing, as you know, how to introduce things like this. So how you can, from the time symmetric equations like a Schrodinger equation or Newton equation, how you can go to the time antisymmetric equations, like, for example, master equations in the quantum theory or quantum systems, or equations of classical statistical mechanics like Boltzmann equations and things like this. Okay, so I think that would be it for the theory for today. So for the tutorial, I'm going to give you an example of particular master equation for the two-level system, which interact with the thermal bath, but I will just give you this equation, and we're going to try to solve it in the various ways. And in the home assignment, if you wish to do it, there will be some other equations, which I will suggest that you follow. Do you have any questions? Okay, it doesn't seem to be the case. Okay, so I will stop sharing my iPad. We might come back to it because there will be a couple of little derivations which we might do. But now let me just go to and share my course screen. Okay, share screen. And what I want to share, probably Firefox. Okay, do you see my Jupyter notebook? Can you please confirm?
Yes,
cool,
we
thank
can
you.
see it.
Wonderful. Okay, so first of all, yes, I'm starting by importing some standard libraries, which you already seen kind of during the last 2 weeks. So NumPy, matplotlib, and I define a couple of standard matrices. So we're going to need to use something which is called the sigma z matrix, which is just a diagonal matrix. And the difference from the identity is like identity have 1, 1, and this is 1 minus 1. So very simple. And something just called sigma plus and sigma minus matrix. Sigma plus is have only 1, 1 in the upper corner, and the sigma minus have a 1 in the lower corner of diagonal. Yes, and exactly as I wrote to you on the kind of on the iPad. So if I have a two-level atom and it's interact with the thermal environment, so it's kind of it just kind of in the contact with the thermal environment. If we leave it to relax, so and if we want to, and if all the conditions for the quantum master equation in the Markov form are satisfied, so what we're going to have, the master equation, which is looking like it's shown here. Yes, so d rho by dt is equal to L rho, and where the L rho is exactly in the form as I wrote to you on the iPad. So we have some Hamiltonian part, and this is just a free Hamiltonian of the two-level system. And we have two terms. Ones are which are doing sigma minus rho sigma plus, and another which is doing sigma plus rho sigma minus. So what is term sigma minus rho sigma plus is doing? It's taking two-level atom and bringing it down. So what this term is describing the process of the losing energy by the. Do you see my cursor?
Yeah.
Okay, so this term is describing to us the process of the losing energy by by the two-level system, while this term is describing how we're gaining energy from the system. And this little coefficient n here is the so-called Bosens-Einstein thermal coefficient. Okay, let me just probably just add it here. So n. So n is just equal to, it's a fraction. It's essentially your standard Bose-Einstein function. And what you have here h bar omega. Okay, in this case, omega 0 divided by the k Boltzmann t. And here you have also -1. Let's see. Yeah, okay. Okay, so, and what does this describe to you? This coefficient, it describes you how many thermal photons or how many photons in the environment are available on the given frequency omega of the two-level system. And another interesting thing is that when your temperature is absolute 0, so when the T is equal to 0, you can calculate this limit. You get that the average number of thermal photons will be 0. So you're losing this term, but you're going still to have this term. And the action of this term will be driven by this coefficient gamma. And that's why this coefficient gamma, which is temperature independent, is called spontaneous emission coefficient, because it describes you how you're losing energy irrelevant of the temperature. And when you multiply it by the average number of photons, sometimes it's called thermal fluctuations, because that's the describe you the measure of the energy which you are getting or losing to the system due to the fact that your environment have temperature. But even if it's 0, we're still going to have this term. And that's exactly the term which is responsible for the fact that if you have a real atom, you excite it, you're at 0 temperature, you leave it, and the atom will 100%, whatever you do, it will emit the photon or multiple photons if it's a dipole forbidden transition. For example, like if it's from 2s to 1s transition, it's coming through the 2-photon emissions. So in that case, whatever we do, we're going to go to the ground state. And that's what this term is describing to you for. Okay, so, and what we're going now to do, so the density matrix here is just 2 by 2 matrix, which have, of course, it depends on the 4 in general case complex parameters. And I'm going to do against what the lecturer in the morning session warned us. So I'm going to invent bicycle, because sometimes it's just nice to invent bicycle. And we're going to solve this equation numerically using the Runge-Kutta method, which we're going to program on the way. And so the first what we wanted to program, we want to program function, which is going to take in matrix 2 by 2, which is x, and spit in us this thing. Okay, so this is taking linear emission x. It depends on the frequency omega 0, number of thermal photons 2. In this case, is just, you can choose any other number, and the gamma coefficient of spontaneous emission, these default parameters 0,01. And essentially what I do, I just calculate this lengthy expression and spitting it out. Now, if you just go to Wikipedia and you check Runge-Kutta of the 4th order, you will get these conditions. And the only simplification which I do, our right side of the equation is time independent, so we just ignore the time dependent terms, and we're going to get this iteration. Okay, let me restart the kernel and run it on the fly, because it definitely will work, hopefully. Okay, so now we need to choose some initial condition. Without particular serious reason, I just choose the condition where we have so-called, it's a pure state, plus state, and the plus state is the eigenvector of the sigma x, and it's looking like this. Okay, so, and now what we just want to do Runge-Kutta iteration. So what do? So we have our initial condition, it will look like this. Our initial time 0, our final time 20. We're going to divide it by the 500 steps. So we can calculate what will be the iteration of the steps. So final minus initial divided by the number of steps. And now we need to store somewhere solutions. Yeah. So solutions are 2x2 matrices, and we're going to store n+1 of them. Why n+1? Because in the first one, we're going to store initial conditions, and afterwards, we're going to do 100 iterations. And it's straightforward. We go from 1 to the end of our array for the until n step +1. And we're saying that the next step is equal to the Runge-Kut applied to the previous step. That's why we're starting from 1, because we apply to initial condition. So we've done it, and yes, it's a 2x2 matrix. It's done very quickly. So now we can do matplotlib and assume that you've seen it already. So what do we have here? So I create a little range for the times, and because it's a good behavior to measure time in dimensionless units, I'm going to measure time in the units of this coefficient gamma t, and I choose here by default gamma is equal to 0,1. That's why I choose my range to be from initial to final number of steps, but I also multiplied by 0,1 by gamma. So now this is my gamma t, array of gamma t's. And what I'm plotting the elements of the density matrix. I have 2 elements on the diagonal, row 1, 1, row 2, 2. And I also plot, because here we don't employ the fact that the trace of the density matrix should be 1. So it's very nice to check that our numerical simulation doesn't go crazy. So that's why we also plot trace of density matrix. So that's element 1, 1 plus element 0, 0. And we also plot, because we have 2 identical off-diagonal elements, yes, kind of the complex conjugated, row 1, 2, and it's equal to the row 2, 1 complex conjugate. So I just plot real and imaginary part of the off-diagonal element. Yeah, and obviously, yes, we're getting exactly the same image as it was here. So row 1, 1 is looking like this. Row 2, 2 is looking like that. It's thermalizes quite quickly, because you see somewhere here, nothing happened to the diagonal elements, while there is a lot of still oscillations and much slower thermalization in the off-diagonal elements. And the little kind of consistency check that our trace of the density matrix is pretty much equal to 1. Probably, if we go closer and if we just plot the trace, we can see some wiggling. But as long as it's within the error range, I think it's good enough. Okay. So, and you have this code, so you can play with the code if you want to. Okay, so, and what I wanted to do in this tutorial, I want to show you that the same equations could be solved with the different approaches, including the approaches which were presented to us by the morning lecturer, to show that that yeah, if we want to use SciPy, we can also use SciPy, but sometimes you want to do a little bit of invention of the bicycle. Okay, so any questions by this part of the tutorial? Okay, you can play with the code and maybe ask the questions next time. So the second approach is looking like this. So our master equation is looking like this, and it have a formal solution. So if our super operator is time independent, and in our case it is, formal solution is looking like this. We can write that the row of t is exponential of this, exactly this dynamical map v of t on row 0. And what does it mean, exponential of the super operator? It means we just need to calculate the sum like this. And it's rather difficult to calculate the sum like this. But instead of doing that, what can we do? We can say, and this first equality is it's a strong equality. So row of t plus h is equal to e to the hl on row of t. So this is no approximations, because if we get here t plus h in this, in the argument of the exponent, because L commute with itself, because it's a time independent, we can always write it as a product of the two terms and act only with a TL on row 0 and get row of t. But what we're going to do next, we're going to do approximation. So we're going to say, okay, we can do exponential expansion, but we're going to take not all infinitely many terms, because it's a little bit difficult on the computer, but we're going to take only m terms, and the number of terms will depend on the level of approximation. Yeah. So, and because we were doing with you something which is called Runge-Kut of the 4th order, so it means that your error is supposed to scale to the 5th power of your small parameter h. Here we're going to do the same just for the pure comparative purposes. Yes, so the only thing which we need to change in order to see how it works, we need now to do an implementation of this step. And how it's done, so I also create a little function which I call exponential step. Yes, so kind of it's eating up our density matrix rho of t, small step h, and m steps of the sum, and it will spit out to us rho of t plus h. So essentially, what do we need to do? We just need to calculate this sum, and that's where we can play a little tricks which are related to the memory. In which sense? So if we go back to the Runge-Kutta method, so when I'm calculating a step of Runge-Kutta, yes, I'm coming with the x. So, and if my matrix is very large, so I need to store x. Now I need to store another 4 copies of x, or objects which have the same dimension as x. And if you're doing really kind of, if you're pushing the boundaries of what your computer or your supercomputer can do, this could be too much. So what you can do in that case, if you have a time-independent super apparatus, you can do this. Why you can do this? Because you don't need to store 5 objects simultaneously. You can store only probably 3. Yes, so because we have x, we have temporarily x, and res. Yeah, so we can do it like this. Okay, I already defined it, and we can check the same game, the same initial conditions, initial time, final time. So, but now we're using the solution will be with our exponential expansion. So for the step, I'm not using the Runge-Kutta, I'm using the exponential expansion. And I can do the plotting again. And boom, we get absolutely the same graph. And if you're not convinced, you can play around and try just to put them on together. But I think they look pretty identical. Okay. So now in the morning, we learned with you that we shouldn't invent a bicycle, even if we have done it just now twice. Let's use the SciPy integrator. But we cannot use the SciPy integrator straight away. So what we need to do, we need to create a function which is going to treat this density matrix as the vector and spit out as iteration. So in that case, what we need to do, we need to go from the equation like this to the equation for the kind of vectorized form of the density matrix. And one can do it straightforwardly. So for that, you just substitute into this equation. Instead of rho, you substitute 2 by 2 matrix, which have rho 1, 1, rho 1, 2, rho 2, 1, rho 2, 2 elements. Instead of sigma z, you substitute this matrix, sigma plus, sigma minus these matrices, and you just do the brute force calculations. And after you calculate it, you were going to get a 2 by 2 matrix from where you can identify the right side of the equalities. And if you do it correctly, you're going to get 4 equations like this. So now we're ready to do the function for the SciPy, which is going to take on input current values of the elements of the density matrix and spit you out the iterated one, or spit you out not the iterated ones, but the derivatives of them. Okay, so this is just the pure copycatting of the Martin's code in the morning session. So now we're substituting the same initial time, final time, number of steps to have the consistency, initial condition. Oops, I don't think that I'm running this. Yeah, so we form a vector, and afterwards now we get here a solution, and we can again plot this solution, but as you see, it looks identically the same. Okay, so what can we learn from that? Okay, that first of all, there are multiple ways of solving things. Okay, if we want to do it using the, I don't know, SciPy integrator, we can always do it. But sometimes, you know, there are situations when you might consider do not use built-in solution. So when you have a very large problems and you need to control how much memory you spend and things like this, sometimes not using built-in solutions might be an advisable thing, but it would be very nice to see first on the simpler examples that you are getting identical answers. Okay, so, and now speaking of the resources, there is one more way of solving the same problem. And that's use the fact that all these three solutions which I've shown you are extremely wasteful. Why they're wasteful? Okay, there is a message in the chat. Okay, sorry. Why they're wasteful? Because we're talking about the density matrix, which depends on four numbers, which in general case we're dealing with the four complex numbers. Yes, because like if we program it, it's a four complex numbers. So it means that it's 8 real numbers. But in fact, what do we need? We need only 3 real numbers. Why we need only 3 real numbers? Because on the diagonal, we have real numbers only because it's the probabilities and they sum up to 1. Yeah, so it means that it's 1 real number. And the off diagonal, row 2, 1 is complex conjugate of row 1, 2. So in order to describe row 1, 2, we need only 2 numbers. Yes, so we need 2 real numbers, real and imaginary part of row 1, 2. So as the result, in order to describe all possible degrees of freedom of this system, we need only 3 real numbers. And the question is there any way how we can efficiently map it from 8 numbers to 3? And of course, we might say that, okay, in this situation, it doesn't really matter because, I mean, 3 8 numbers, your cell phone can do it. But, you know, if you imagine that you are dealing with the system which have kind of n by n, and if n is large, let's say a couple of thousand, and in this case, you really need to sit down and start counting. So if you, for example, want to describe some very large spin systems, and by whatever reason, you cannot use some fancy matrix product state, for example, you have a highly excited states and things like this, but you still want to describe it. So in that case, you will really need to count how much memory you spend. Okay, so and what can we do in this state? In this case, we can go from density matrix to parameterization of density matrix through the observables. And for the 2-level system, it's a very nice basis that we can relate how this 4x4 density matrix will depend on observables of the Pauli matrices, sigma x, sigma y, sigma z. And you can always write it like this. So it's 1/2 of identity matrix plus R on sigma, where sigma is the vector of the Pauli matrices and R is the vector with this kind of 3 observables. So x, y, z, and each of them is just equal to the trace of the density matrix, which with corresponding Pauli matrix. So you can just do the substitution, find the trace, and you're going exactly to get these x, y, z's. And now playing absolutely the same game, but instead of row of t in the form of row 1, 1, row 1, 2, row 2, 1, and row 2, 2, if you substitute 1/2 of identity on R on sigma, you play the same game of calculating what the action of the semigroup generator, you're going to end up with the 3 differential equations for the real quantities because observables are real. Yes, so first of all, we need to find 3 functions which are real. Yes, so kind of we don't need to take care about, you know, the errors which are coming from the fact that we're dealing with the complex numbers. And we also know that as observables, they're bounded. And in this case, they're bounded between -1 and 1. So it's also relatively easy to keep track of them. And what we can also say very easily, we can say something about the steady state solution of this system, because steady states happen when the time dependence is equal to 0. So derivative is equal to 0. And we can see that from these 2 equations, x and y components are equal to 0. And there will be only non-zero z solution, and it's going to be negative. And that is perfectly fine and nicely agreed with the thermodynamics because that's what you expect. What is observable z? It's telling you what is the difference between the population of excited state minus population of the ground state. And what we've seen with you in the semigroup generator, that the population of the probability to go down is slightly higher than the probability to go up due to the spontaneous emission coefficient. And so that's a little difference is exactly what will be responsible for the fact that if we take this equation and equate it to 0, the steady state value of z is going to be negative. Okay, but now let's program it into the SciPy and apply the SciPy integrator. So we have an input z, x, y with our values of the possible omega Thermos number of photons and the gamma. So, and exactly again, copycatting the code of Martin, I create this function. And now we can just do again the propagation. We need to recalculate initial conditions, form the vector, and plot the solution. Okay, first of all, we could see that the solution is looking slightly different, yeah, or roughly speaking, slightly different. And the reason is very simple, because we're plotting different things. Because here we're plotting elements of the density matrix, and here I'm plotting observables. So if you want to relate between sigma x, sigma y, and sigma z, or x, y, z in these notations, what you need to use the fact, you need to use the density matrix as the kind of rewrite it in the way how it's written here, and see what will be rho 1, 1. And rho 1, 1 will be 1 plus z divided by 2. So if you take a graph for the green graph, add it to identity and divide it by 2, you will get exactly curve which is going to look like this. So to get rho to 2, you need to take 1 minus sigma z and divide it by 2. And it's obviously when you do minus sigma z, you inverse it. So you have something like this. And of course, plus 1/2 will give you a shift. So you're getting exactly something like that. And you can make a similar argument for the real and imaginary part of rho 1, 2, because sigma x is rho 1, 2 plus rho 2, 1. So this is two real parts of rho 1, 2. And these two graphs for the sigma x and for the real part of rho 1, 2 are exactly differ by the factor of 2. But you can do numerical experiments just to put it one on top of the other to see that you're getting absolutely identical descriptions. Okay, so that's it from my side. And there is a little home problem for you, and it's deal with a slightly different master equation. And this is the master equation for the two-level system, which is weakly driven by the kind of external classical electric field, so kind of your laser field. And it's kind of the reservoir here, it's at 0 temperature. That's why we have only term which is describing to us emission. But in the Hamiltonian, we have not only sigma z, but also we have a sigma x, which exactly describe to us classical driving, where the omega is the frequency of the driving, and the omega d, so omega is the amplitude of the driving, and here instead of omega 0, we have a difference, omega 0 minus omega d, where the omega d is the frequency of the driving field, or kind of laser field. So on what I suggest that you try doing, you try to adopt all the codes which I have here for this equation. So, and this is relatively easy. You can just play with the parameters, and you can choose some default parameters, and you just need to change essentially one function or two functions. What is more difficult is to find the equations for the XYZ observables, but for this equation, and adopt it for the SciPy code, which we have here, because that will be the different set of equations. And in order to get that, you probably need first to try to get this set of equations. Yes, and also you can also in this situation as well, you can find the steady state for these observables X, Y, Z. So you can solve the corresponding system of equations when this side is equal to 0, and you can find what will be the steady state values, or kind of what to which populations or to which state the atom is going to be driven by the weak field if you just let it drive it for long enough time, so that the system is coming to some sort of it's called non-thermal equilibrium, because you get an equilibrium between the driving and kind of driving is bringing you energy, and the dissipation is taking away energy from the system. So you come into this non-equilibrium, so-called non-equilibrium steady state. Okay. Are there any questions?
There's some.
Yeah, I see. Thank you. Yeah. Could you please explain the effect of gamma coefficient in the interaction between system and the bath in the Gksl equation? And if the gamma is negative, we cannot have not the semi-definite, but the semi-group property. Yes. So essentially, yes. So kind of I will explain in the next lecture a little bit more about what is the gamma coefficient and where it's coming from. It depends very strongly on your model interaction between the system and bath. So kind of if for example, you describe how the two-level system is interacting with the environment, but just in a free space, you get one equation for the gamma coefficient, and this is called spontaneous emission coefficient. And if you open the standard textbook, for example, Zetterli, quantum mechanics Zetterli, I don't remember how to spell it correctly. If somebody, Francesco, can type it, that would be probably perfect. So over there is a whole kind of in the chapter which is describing closer to the end of the book, where it's describing the interaction between light and matter in the dipole approximation. This formula is derived, how the spontaneous emission coefficient for this type of transition is looking like, because it's very strongly model dependent. But generically, what you want them to be positive in order to have a quantum master equations in the Markov case. Yes, certainly. Okay, perfect. Thank you, Francesco. And if the gamma is negative, what you will have that you're not going to map density matrix to the density matrix. What you can have from time to time, and this is from the one definition, it would be still called Markovian open system. From the other definitions, it wouldn't be called Markovian coefficient. You can have these coefficients gamma k, they will be time dependent and they will oscillate. And from time to time, they can become negative and afterwards positive again, and they can oscillate. And in this case, what you can have the kind of being them negative for a little time. And that is still okay, because if overall you can define kind of some measure, if you overall have something which is called completely positive map. But what is completely positive and why completely positivity is very important and why these semi-group forms are very important, I will told you on the next lecture, because if I would tell it to you today, we wouldn't come to the tutorial, and I'm trying to have half of the theory, half of the time some programming if it's possible. Okay, so is there a specific reason why the Runge-Kutta was used instead of other numerical methods? No, Runge-Kutta is just, it's a vanilla standard in the ordinary differential equations. Of course, one can get more sophisticated and derive some, other numerical methods with the changing step and things like this. But that will be exactly the situation when I will follow the advice of Martin, the lecturer from the morning session, who says that don't invent a bicycle. If Runge-Kutta doesn't satisfy your requirements, maybe you want to use the integrators which were developed by community and which was checked by community. But having a Runge-Kutta is just, I just go to Wikipedia, see how it works, I do it, and as you see that there is no difference between the solutions which are produced by Runge-Kutta written by me or Runge-Kutta written by the SciPy community, or just doing that direct exponentiation. No particular reason. I have no affiliation to neither to Runge nor to Kutta. Any other questions?
Ilya, there doesn't seem to be other questions. So since we already went also 10 minutes over time, maybe this is a good time to stop for today. And I'm sure if the participants have questions, they can ask you in 2 days when they will see you again, or just post something on Moodle or in the WhatsApp group or whatever.
Yeah. You can post on the Moodle, and so in the worst case scenario, if there will be something very urgent which could not wait for 2 days, I can always record a little video on the iPad and post it to the Moodle back. So feel free.
Yeah, that's perfect. Thank you very much, Ilya. Thank you. Yeah. And Daniel, thank you very much as well for introducing Ilya this morning and this afternoon and taking care of the session while I couldn't be here. Yeah. So Ilya, thank you very much for a good start of this is the last lecture series. So now we had the first lecture of all the 4 lecture series, and tomorrow we start with the iteration of the lectures number 2. Yeah. Perfect. Then I wish you all a good afternoon and lots of fun with Python. Yeah.
Yeah, just download the code, play with the code, and enjoy it.
Just have fun, and next time you can give Ilya some feedback or using the Moodle forum or the WhatsApp group. Yeah, perfect. Thank you very much. Have a good afternoon, and Daniel, thank you very much again. Ilya, thank you very much, and thank you to all the participants that have been with us this afternoon. Perfect. Thank you very much.
Thank you.